Good morning, everybody. Thank you for being here. My name is Mike Marin.
I'm Carlos Beltran.
And today we're going to talk about the pipe. So with regards to time, we want to go ahead and just get started with the pipeline enhancements. So there are 5 stages to the pipeline. There's fetch, decode, execution, the memory stage, and the write-back stage. And between each stage, we have a pipeline register that carries information across. In addition to those pipeline registers, we have 3 control units. There's the data hazard, the control, and the forwarding unit. We're going to go ahead and start off with the control unit. So this is an overview of the control unit's visual representation. The control unit lives in the decode stage. This is where all the control words are generated, and they are passed down through the pipeline. And they are used in their appropriate stages as they move along the pipe.
So this is a detailed schematic of the control unit. Just to make the control unit a bit simpler, we decided to make all of the control signals 32 bits, but not all of the 32 bits are being used. So this is just an example of how they're encoded in the 32 bits. This is for the control, ID control, EX control, memory control, and write-back control. This is showing the forwarding signal. So the forwarding signal is a 32-bit signal composed of the destination and source operation addresses for that current instruction. The stall, stall 2, and flush signals are being used to clear the control signals as well as to encode an acknowledge signal within the write-back state, or write-back control. This is an example of an addition instruction. As you can see here, we set the control words for that addition instruction for each state, and the forwarding forwarding signal is being set according to what the addition requires, which is the S, the T, and the D registers.
So this is just a representation of the decode stage. As mentioned earlier, the control unit does live in this stage, and all the registers are being read for the current instruction. The next topic is the forwarding unit. Now the forwarding unit generates the selects, and you can see here on the orange line, so you can see that there. And they're generated by the forwarding control. And those are the green lines coming from the control. This is the Verilog on how those selects are generated. You get the execution operations, or the source operations from the execution, and you compare those with the destination operators of both the write-back and the memory stage. And if the conditions are met, they set the flag to high.
So this is an example of forwarding. As you can see in this example, register 1 is data dependency. So the forwarding unit forwards the data for register 1 from the end of the execution state to the beginning of the next execution state. In this example, again, register 01 is a data dependency. So the data is forwarded from the end of the memory stage to the beginning of the next execution state, of the third execution state, where it's needed. So in this example, register 1 is data dependency, again, but it's being used in the store word as the data being stored. So the data is forwarded from the from the end of the execution state to the beginning of the next execution state, but it's not actually being used until the memory stage. And finally, in this case, register 1 is also a data dependency, but the forwarding unit does not have to take care of it because the data is being written to at the negative edge of the clock in write back state, and it will be available in the instruction decode stage. Yeah, so the forwarding unit also takes care of flush flags, which is asserted when a data dependency happens after a load word. And it is done this by comparing the forwarding signals in the instruction decode, and the forwarding signals in the execution stage, as well as the instruction in the execution stage. So this is just a little snippet of the code. As you can see, it's comparing the source addresses with the destination addresses, as well as checking if the execution address is a load word. This is an example of that. So because there's a load word before the addition, and because register 1 is data dependency, the forwarding unit detects this and sets the flush signal, which inserts a no-op state so that the data can be forwarded from the memory stage to the execution stage.
Here's the execution state. It's just a visual representation here. It executes all the operations using the appropriate resources available. So you can see from the control, the signals are moving from one pipeline register to the next, as well as the output of the ALU is going to the next stage. And that next stage is the memory stage. And similar to the previous one, the control signals are also passed from this stage onto the next, as well as the outputs from the data memory. And that next stage, of course, being the write back stage. And in this this stage, the destination register gets written to on the negative edge of the clock, depending on if the instruction requires that. So the next is data hazard. And data hazard implements a few things. Those are the branches, the jumps, the interrupts, as well as asserts and deasserts stall stages. So this is just a visual representation of where the data hazard lives and how it ties into each stage on pipeline.
So the first thing the data hazard does is implements branches. So all of our branches are being done in the execution stage. The processor uses the ALU to calculate the operation required by the branches, and the data hazard uses the zero flag generated by the ALU to determine whether or not the branch passes or fails. So if a branch is executed, the PC gets loaded with the signal required, or the signal generated, and the data hazard implements a stall signal, which clears the control words until the stall acknowledge is read in the write back stage. So there's an example of the branch. As you can see, the branch is being carried out in the execution stage, followed by stall stages until the stall acknowledge is read in the write back stage. So our pipeline takes three stall stages to execute a branch. The last thing it does is implements jumps. So jumps are carried out during the memory stage. All of our 3 jumps are carried out during the memory stage. PC again gets loaded with this value. And the stall 2 signal will be asserted, clearing the control signals and encoding a control acknowledge, which will be read in the any clock after the write back stage. So this is an example of our branching of our jumps. Our jumps are being carried out in the memory stage, followed by 4 stall stages. Followed by stall stages until the stall acknowledge is read in the clock after the write back stage.
Are you going to explain why it took so many stalls?
Yeah, so technically, since we are jumping in the memory stage, we decided to jump all of our 3 jumps in the memory stage just for sake of simplicity. Some jumps can be done in the instruction decode stage, but we just decided to do everything in the memory stage. Technically, we could have taken 3 stall stages, where the next instruction fetched could have been here, but we ran into the problems of timing, where we figured it was because PC needed to be loaded and in the registers, instruction registers needed to be loaded, so we just added an extra stall cycle for everything to settle down.
So that may have been a simulation problem versus a
Yeah.
hardware problem. Okay.
Yeah, we were having a couple of those.
Yeah.
So the next one we're talking about is breaks. And so breaks flags is read and carried out during the execution stage. Just over here. And during that time, the PC increment and the IR outload are deasserted, and the stalls are asserted until we get a reset because of the break. This is an example of a break. As mentioned before, the break happens in the execution state. You can see here by the green coloring. And the instructions that are in memory and the write-back stage need to be carried through. And the instructions that are in the fetch and decode, if any, those will be flushed out. And the rest of them are no ops because of a break.
This is our instruction fetch stage. So during this stage, the pipeline, during this stage, the PC can either be loaded or incremented with the appropriate signals. The instruction memory can be read, and the pipeline registers can be loaded.
So next we have the I/O module, and the I/O module lives in the memory stage. So the memory and the I/O is either being read to or written to or read. And the interrupts are generated by the I/O module, causing the data hazard to stall the pipeline, as well as execute the stall RTL right here.
So to verify our pipeline, we decided to run this little instructions composed of a couple of add immediates and add and subtraction. First of all, you can see these are our instruction registers for each stage, and these are our registers. So right after a reset, the first instruction is not actually an instruction being fetched, but rather it's the stack pointer being initialized. Then following that is all of the instructions being fetched and the instruction being passed through the pipeline. So the first instruction, the first register being loaded is register the stack pointer with the value 3 of C, and then add the negative edge of the clock, and then every following negative edge of the clock, the register is being written to. So this is a timing comparison of our pipeline and our baseline for all 13 modules. And this is the same data, just shown in the chart. The gray is our baseline and the blue is our pipeline. And I believe we're getting somewhere around 60 to 70% faster. Yeah, it could have been faster, it's just the jumps and the branches weren't efficient.
So we thought we'd end with a quote, and we found one that I thought was kind of relevant to all of us. And it's, computers are incredibly fast, accurate, and stupid. Humans are incredibly slow, inaccurate, and brilliant. And together they are powerful beyond imagination. This was a quote by Albert Einstein. So, thank you for your time.
Any questions? Excellent. Thank you.